So we just talk about when the function is continuous at a, we can just do a direct substitution and substitute a into x to find the limit, right? And the limit will be equal to f of a. So what type of function have this property? So what type of function are continuous? So the following theme is going to talk about some type of function that are continuous on the domain. Okay. This theme says that if function f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So the first one is the sum of the two functions. So basically it says that the sum of two continuous functions is continuous. And here say the difference of two continuous functions is continuous. And there's a constant multiple of a continuous function is continuous. And the product of two continuous functions is continuous. And the quotient of two continuous functions is continuous, providing that g of a is not equal to 0. Okay. So this following type of functions are continuous at every number in their domains. Okay, so maybe I should put the S over here. Okay. So we're kind of interested in what type of function are continuous on the domain, because that way we can just, to find the limit of the function at a, we can just go ahead and substitute a into x. So that will be just equal to f of a, right? So what type of function are continuous at every number in the domain? In other words, those functions will have no break in the domain. Okay. Number one, polynomial function. For example, this is a polynomial function. What is its domain? And some of you said it's all real number, right? Yes, all real number, or you can write down -infinity to infinity, this open interval. The second type of function that are continuous on their domain are rational functions. This is a rational function. It's polynomial divided by polynomial. What's the domain for this function? The domain of a rational function will be all real number except those numbers that make the denominator equal to 0. So the domain over here will be all real number except 1. So if you write it in interval notation, there'll be -infinity to 1 union open interval from 1 to infinity. The third type of function will be root functions, square root, fifth root, etc. Okay. Number 4, trigonometry functions, sine, cosine, etc. Number 5, inverse trig functions, inverse sine, inverse cosine, inverse tangent, etc. Notice that this -1 on this upper right corner here is not an exponent. That is not the same as the reciprocal or tangent of x. This -1 over here indicates it's an inverse function of tangent. So this is the same as arctangent. Okay. The sixth type of function are exponential functions, such as 2 to the x, e to the x, 1/3 to the x. And the graph for that will be, if the base is greater than 1, such as 2 or e, then the graph will be exponentially increasing like this. Okay. And when the base over here is between 0 and 1, then the graph will be exponentially decreasing like this. And as I point out in my handout to you guys earlier, so one way to remember is you put them together. When a is greater than 1, it will be like this. And when a is less than 1, and when a is less than 1, it will be like this. And if you put this head over here and a fin over here, so that's look like a fish, right? So I call that the exponential fish. So that might help you to remember the shape for exponential function. Okay. So I don't know if you have tried that before. When we go to Chinatown, we buy fish. We can ask them to chop up the head and also chop up those fins, right? So when you chop them off, you have this pair of exponential functions. Okay, the seventh type of continuous function will be log functions, like base 2 log of x, ln of x, and base 1/3 log of x. Okay. So for log function, when the base is greater than 1. So it's going to be like this. Okay. Now, log function actually is the inverse of exponential function. So if this is e to the x, this one here is ln of x. They are symmetric with respect to the straight line y to the x. Okay, so this is for ln of x. I have the x-intercept here to be 1. And you see the domain for that is going to be all real number greater than 0. So has to be strictly greater than 0. When x equals 0, there's no function value over here. Okay, so domain is all positive real number. Okay. Now remember this graph for Ln. We see that on the handout. Remember from our dance move in the handout. So this is for Ln of x. Okay, that's a graph. Okay, now we're going to go over this example. Where is this function here continuous? Well, it looks like a little bit complicated, okay, function. Well, it does look like a little bit complicated function. However, if we break it apart down to some basic function, so then we can investigate on that. Okay. This one here is Ln, and this is inward tangent, and this is x squared minus 1. Ln of x is continuous on its domain. And what is its domain? The domain over here, it is 0 to infinity, right? Okay. Inward tangent of x is continuous on its domain. Remember, it is one of the type of function, inward trig function is continuous, right? So it's continuous on its domain. What's the domain for this inward tangent? Now, if you recall that from the dance move, okay, it's actually continuous on all real number. The domain for inward tangent x is all real number. So, going to be all real number. Okay. X squared minus 1 is continuous on its domain because it's a polynomial function. The domain for that is also all real number. Polynomial function is going to have domain to be all real numbers. Okay. Now, over here, this function first is the quotient of this and that, and later on, this part here in the numerator is the sum of these two functions. So the sum of these two continuous functions, again, is continuous, right? So this numerator here is a continuous function on its domain. Now divide by this continuous function, quotient of continuous function is again continuous, providing that the denominator does not equal 0. So the sum and quotient of continuous functions is continuous on its domain. So the function f is continuous on its domain. Okay. Now we just need to find the domain for the function. How can we find the domain for this function? We just went over this on page 2 of this handout. Okay. So first, this one here involves the denominator. So we need the denominator does not equal to 0. Well, when that does not equal 0, x will not equal to positive negative 1. Okay. Second, this one involves ln. So this part that you take ln has to be strictly greater than 0. So x has to be strictly greater than 0. And there's no requirement on this inward tangent. Okay. So we need to combine these two conditions here. So x does not equal to positive and negative 1. So we make this a gap. Okay, so it's a gap right here. Okay. And then x has to be strictly greater than 0. So here's 0 right here. But we have to take away this 1. So we're going to end up with this interval union this interval here. So that will be 0 to 1, open interval, union, open interval from 1 to infinity. So that's the domain for the function f. So the function f is continuous on its domain, which is this. So that's the end for this question. Now, another example, we're trying to find this limit over here. Now, we want to see, can I do a direct substitution? Well, if the function here is continuous, then we can do a direct substitution. But let's justify to see if this is indeed a continuous function. We know that sine x and cosine x are trigonometry function, so those are continuous. And when you add 2 to cosine, the sum of two continuous functions again is continuous. And now you divide this two continuous function, quotient of continuous function is continuous. So therefore, this result here will be a continuous function. Okay, it's going to be continuous on its domain. So we can go ahead and do a direct substitution here. So substitute pi into x. So that will be equal to sine of pi over 2 plus cosine pi. Sine of pi is equal to 0. Cosine pi is equal to -1. So the result here will be equal to 0. So the limit here will be equal to 0. So as you can see that if we know the function is continuous, then we can just go ahead and do a direct substitution to find that limit here. Okay, right, so let's take a break.